So welcome back, everybody. I just wanted to give you some messages before we begin. This week, and I have first apologized for not having sent the weekly email. Actually, this weekend was one of these weekends where everything went wrong. So my laptop crashed, and then in the stress, I actually forgot to send you the weekly update. But the topic this week is to try to wrap up the central force problem. And today we're going to analyze how the energy relates to the type of orbits which we have. I just wanted to also give you some few messages. So the second midterm is also available. And we are going to discuss that both this week and next week. I postponed the deadline with 1 week, so we have it for Friday the 15th. The topic today, in addition to the wrapping up this gravitational force problem, is also to point to some of the things which you will need to analyze your results in the midterm. I should also add that you find the solutions to basically all the weekly assignments and the first midterm. If you click on this README file here, you will find, if you just scroll down on the different weeks, there is a link to the solution to different weekly exercises. I think I mentioned this in the beginning of the semester, but I just wanted to remind you about that feature. So let me show you explicitly where you find it. So if you go back to the weekly material, which you will find in the README file. So if we look at that one, and you just scroll down here, you come to the weekly schedule. And what you will typically find is something like this. You will find the solution of the first assignment, and then it goes down all the way till basically the last weekly assignment which we had. So if you just scroll down, you will find typically solution 6th assignment, 7th, and so on. So obviously there's no solution to the second midterm yet. Now the second midterm, if you now go back a little bit, just let me show you where you find it. So if you scroll down on the same page where we have the weekly assignments, for those of you who are a little bit impatient, you will also find the last weekly assignment, number 9, which essentially rotates around what we've been doing now, but it has also an additional exercise about Lagrangian formalism, which is going to be our last topic this semester. And you will also find the second midterm here. And if you scroll down, what you will see now that one of the things you will need is to bring back to life the program which you wrote in assignment number 5. And these exercises are, to a very large extent, numerical exercises, where you are going to use your program and analyze the physics. What does the physics which you get, what does that mean? So one typical example which you will find in this in this second midterm, like if you look at this exercise 110, so we start with a inverse square force, minus alpha divided by r squared. You can play around with the power of r. And what you're going to observe then is that the orbits may not be stable when you increase the power of r. So this is a kind of indication that if the gravitational force had another r dependence, it is not likely that the solar system would have been a stable system. And that's an interesting conclusion. So these kind of things are things which you can explore with the software which you have developed. So the second midterm, there's not much paper and pencil. It's actually you bringing back to life what you did in homework number 5. And if you are not too happy with the program you wrote, you can go back and look up the solution to homework number 5, and then look at the code which is there. So we normally recommend in this case to run things in Cartesian coordinates, because that typically makes life easier when you're going to analyze a problem. Now, the second part of the midterm is actually about you trying to build up a program for the solar system. So last year when I had a poll of what people wanted to do, I think basically 90% of the people wanted to actually write a program for the solar system. I think that's an interesting challenge. It's actually doable, and I've seen that every year. And we start with just adding Jupiter, and we play around with different masses for Jupiter. And then we add gradually planet by planet till we have a program which simulates the solar system. I think it's fun. So I'm not sure whether you will think it's fun, but I hope so. And it's a typical example where you are going to apply what we have gone through to simulate a real system. And it's also in a way, to me, it was very satisfactory the first time I wrote such a program to actually see that, one, I'm able of doing it, and then you can simulate something which we see every day, basically. Okay, so the second midterm is there, and I'm actually going to send, after the lecture today, I'm going to send the weekly email with all these indications. I also wanted to add one small thing, because I realized that people may have forgotten about it. So if you go back to the main GitHub site, you will also find a link, in addition to the weekly slides, you will find a link to the collected lecture material. And there you will also find the weekly schedule with the link to videos and handwritten notes and everything. And you also have a more, how to say, a more coherent collection of the teaching material, which we have also presented in terms of weekly slides. So the material today, which I'm going to go through, is actually not fully in my notes, but it's extremely well covered by chapter 8 of Taylor's textbook. And I really recommend to take a look at chapter 8, and especially also when you're now going to look at the second midterm. Okay, so let's switch back to the whiteboard and try to make this link, which we mentioned, where we now link the energies which we get with the type of orbits which we're going to see here. So let me change to the whiteboard, and please, again, don't hesitate to ask questions in case you have some questions or things are unclear. So any questions so far? So everything which I said now is going to be rewritten in terms of an email, the email which I didn't send during the weekend. I apologize for that. But let's now try to make these connections. And what we did on Friday was actually to demonstrate that we could gain, or we could obtain, elliptical orbits. So what we have are the following equations. So we have an equation for the radial acceleration, which we wrote like this. And this is given in terms of the radial component of the force. And then what we had in addition is this term which we rewrote in terms of the angular momentum, which is conserved, divided by mu, and then we have r cubed. And then we have an equation for the angular velocity, which is given now in terms of, so this is a d phi dt. So these are our two variables. And that is given in terms of the angular momentum divided by mu, which is a reduced mass. What we have done is a transformation to relative coordinates. No, sorry, to relative coordinates. So x is the relative position in the x direction. R is the radius, which represents the relative distance between two objects. And then we have the y component, which is r times sine of phi. What we found is that for the type of force which is given by minus alpha divided by r squared, which is an example of the gravitational force. It could also be the Coulomb force, or any force which goes like the inverse squared distance, relative distance between two objects. So if you see a problem like this in physics, then the solution for the variable r as a function of phi is given by this constant c of 1 plus epsilon times a cosine phi. And where this constant c has a value which is given by the angular momentum. So the c is given by the angular momentum squared divided by mu and divided by alpha. So this alpha could be the masses of the two objects we are looking at, which interact, and the gravitational constant. Or if we are looking at a Coulomb force type problem, it could be the charges of the two particles and 1 over the permittivity in vacuum. So these would be natural constants which define the forces. So in our case, the force is now given by the gravitational force, and we actually have an analytical solution. And one of the things we found is that when epsilon is equal to 0, then we had a circular motion. When we then looked at the case when epsilon is less than, larger than 0, but less than 1, then we ended up with an elliptical motion, elliptical motion. And the topic which we are going to deal with today is actually to link these types of motions with the energy of the system. So let's try to do that. And the thing which we want to do is actually to link this with the way this effective potential looks like, V of F of R, which in our case looks something like this. So we have a minimum here, where we now found that R dot, the second derivative of the radial position, is equal to 0. So the radial acceleration is equal to 0. And this corresponds to the case of epsilon equal to 0. So the energy the system has here corresponds to a situation where we have circular motion. Now, one of the other things which we did, let me just bring this up a little bit, was now to find when we had epsilon larger than 0 and less than 1, what we found then, and now I'm just reminding you of some of the results. So we found that we had an R min, which is given by this constant C of 1 plus epsilon. And then we had an R max, which is given by C divided by 1 minus epsilon. And this particular case, if we now link this with the graph here, it means that we would have an R min here. This is our R min. And then we would have an R max here. And in both cases, we have an energy, a total energy, which is smaller than 0. So this corresponds also to a case where E is less than 0. And we call this for bounded orbits. So this would correspond to the R max value here. So when we now look at these cases, what we have omitted are cases where this epsilon is equal to 1 and where epsilon is larger than 1. So let's try to look at what kind of orbit we can expect when epsilon is equal to 1, which is a case which we haven't looked at yet. So I'm going to do two things now. So one, I'm going to look at these cases with epsilon equal to 1 and larger than 1. And then I'm going to show you that this leads to a parabolic type of orbit and a hyperbolic type of orbit, respectively. And then you're going back and we're going to link that with the energy which the system has, so that we can go back to the graph which you see here of the energy, and then simply say that, okay, if we have this type of motion, that corresponds to this and this type of energy. And that leads to specific values of this eccentricity epsilon. So this eccentricity epsilon tells us, for instance, how much elongated an ellipse is. So if we have epsilon equal to 0, this simply becomes a circle. If we have epsilon going to infinity, we have an infinite elongation of an ellipse. So let's see what that means geometrically and also in an energy point, from an energy point of view. Okay, so let's try to bring back the type of orbits. And one of the things which we did, when we now go to the case 3, we're just going to repeat what we did in case of a circle and an ellipse. And we are now simply going to plug in the expression. So what we have is that r of phi is equal to c divided by 1 plus epsilon of cosine phi. And you see now that this r of phi diverges if cosine of phi is equal to plus minus pi. When we put epsilon now equal to 1. So let's so that means simply that we actually have a radius which is diverging here. Let's see now what the kind of orbit we are going to get from this. So what I'm going to do now is simply to multiply away the 1 plus cosine phi. So I'm simply going to multiply here. I get 1 plus cosine phi equal to c. And then we remind ourselves that r times cosine phi is equal to x. So what I have now is simply r plus x equal to c. And then I'm going to rewrite it as c minus x. And finally, then what we do is we square both sides. If I do that, I get r squared. And r squared is nothing but x squared plus y squared. And that is equal to c minus x squared, which then simply is c squared minus 2 times c of x plus x squared. And you see now that the x squared term disappears. So what I get now is I have a y squared is equal c squared minus 2 times c of x. And if I isolate x now as a function of y, what we have is y squared, sorry, not that one, but I have a c squared. So I have a c squared divided by 2c. So I get a 2 here, and this is minus y squared. And this is also has a divided by 2c. And you see now that this is the equation for a parabola. So x as a function of y is proportional with y squared. And this is a parabola. So remember now that a parabola, so you would have something like f of y would be something like a constant a0 plus a a1. It could look like this, a of x. But then we would have an a2 times x squared. And normally a parabola has a1 equal to 0. And that will be the mathematical expression for a parabola. So what we have here is now simply a parabola. Now, before we look at the case with epsilon larger than 1, let's now go back to the energies and try to link the different values of epsilon with a specific energy, which we can read off that curve of the potential energy. So let's now link with energy before we go to the final case, which is going to give us a parabola. So this is before we analyze, before analysis of epsilon larger than 1. So let's take a look at this now. Now, one of the things we're going to assume is that at these points, which we can call for inflection points or turning points. So if you look at this specific point here and this specific point here, what we can assume here now is that the radial velocity is equal to 0. So this is an assumption we are going to make. Now you are free to make that assumption. And that's also going to simplify the analysis which we make. So at R min, so an assumption we make now, assume that at R min and also R max, at R min we have that the radial velocity is equal to 0. So we have only angular velocity at that specific point. Now, what we also have is that the kinetic energy is given by 1/2 of mu, and then it has R, sorry, not divided by mu, but multiplied with mu. It had R dot squared, and then I have plus 1/2, and then I have mu, and then I have R and phi dot squared. So that's the kinetic energy. So that led to a effective potential. When we now go back and look at the expression for the potential energy, so that led to a V effective, where we now have incorporated the angular momentum term. So we got this effective potential, which is given by the potential which we have, plus, and then we have this term which goes like L squared, the angular momentum, which we assume to be a known quantity, divided by 2 mu over R squared. So the total energy, and now we are looking at the total energy at R min. So what we have assumed now is that the radial velocity is equal to 0, but the other two terms are not necessarily 0. Because if we look back at the curve, what we have now is a total energy. So the energy which you see at this specific point is not necessarily 0, and the same here. And that contains potential energy, and it contains also kinetic energies, which comes from the angular velocity in this new coordinate system. So when we look at the analysis in the new coordinate system, what we get then, when we now assume that the V of R, so this is the potential which we're going to plug in, something which goes like the gravitational force. So we're going to have this one minus alpha divided by R min. So we are now looking at explicitly this turning point. And then we have a plus. And then we have an L squared divided by 2 mu of R squared min. So the next thing we can do now is simply to rewrite this. And if we now manipulate a little bit the expressions, we can now rewrite this in terms of 1 divided by 2 R min. And then I have a term which goes like L squared divided by mu times R min. And then I have a minus 2 times alpha. Now, what I know as well is the following. I know that this R min is now given by C of 1 plus epsilon. So right now, I'm not specifying the value of epsilon, okay? So I'm just leaving this in a general form. And what I have assumed now is I've taken the expressions which I got for R min and R max when I did the analysis of the energies in terms of the minimum and maximum value of the radius. Now, if we now plug that in, if we now just plug in the equations, we can actually rewrite this as an L squared. So let me remind you why it becomes like that. So if we go up a little bit and look back at the definitions we had, which is something we defined in the beginning of this discussion of central forces, we have now defined the C as a function of 3 physical parameters. Alpha, which is related to the force, L squared, which is a quantity we can measure. We actually know the angular momentum of the Earth to a pretty high precision. So this L squared is something which we can look up from experimental measurements. And then mu is now the reduced mass. So if you're looking at the Earth-Sun problem, we know the mass of the sun, we know the mass of the Earth. So these are all physical parameters which enter our theory. And if we do that, what we have now, when we just rewrite the equation, is that this becomes equal to L squared divided by alpha times mu, and then I have 1 plus epsilon. So what I'm going to do next is simply to plug in this equation for R min into this equation here, and the same into this equation here. So if I do that, what we get then is simply the following. So we just put this in parentheses, because this is just an intermediate step. So we get the following. We get alpha of mu of 1 plus epsilon divided by 2L squared. So I'm simply plugging in the value for R min. And this is multiplied by alpha of 1 plus epsilon minus 2 of alpha. And I can rewrite this one when I manipulate further. I'm going to get this to be equal alpha squared mu divided by 2L squared. And then I have my value for 1 plus epsilon, and then epsilon minus 1. And this is simply alpha squared of mu divided by 2L squared of epsilon squared minus 1. Now, if we now look at these physical parameters which we have, we know that mu is larger than 0. L squared, if we look at measurements, is larger than 0. And we have also assumed that the gravitational constant multiplied with the masses are terms which are larger than 0. So it means that the physical constants which we have in front here, they're all larger than 0. So what I plugged in now is the value of the energy. So the quantity which you have is actually the energy at this R min. So what we have then is E at R equal to R min, which is now given by alpha squared times mu 2L squared of epsilon minus 1 here. Epsilon is also determined in terms of physical parameters. And the physical parameters, if we now decide that all these parameters are larger than 0, it means that epsilon can be equal to 0 or larger than 0. So this means actually that our epsilon is larger or equal than 0. So that's a constraint which we have. Now, this is the expression for the energy at this R min, but we haven't said where this R min is, okay? So if we go back to the energy curve, what we could have now, and let's just bring it back. So we could now say that R min is this quantity here. So you could think of your object going back and forth between an R min and R max. So this was actually elliptical motion, or it could be at the bottom here, or we could place it here. So we haven't decided yet where we are, or we could assume that we are here, for instance. So this R min is our minimum distance between the two objects which interact, okay? So that's the minimum distance you can reach. Like for the Earth-Sun case, R min would actually be the perihelion for two planets, or one planet rotating around the sun. So if we now go back here and look at the case which we have, so if the energy is smaller, is less than 0, so if E less than 0, we have already analyzed the case where epsilon is 0. That gives us circular motion. So the case which we are interested in now is epsilon larger than 0, but smaller than 1. So that's the first case. Now, if that's the case, what we have is an equation which has to be satisfied, which is given by 2L squared. And then I can actually rewrite it as an epsilon minus 1 times an epsilon plus 1 less than 0. So that's the first case. Now, if we do that, here, what we haven't done yet is that we haven't defined this one. So we haven't said anything about that. The only thing we are saying now is that the energy is less than 0. Now, we can choose whether we want to have this larger or equal to 0, which gives a circular motion, or less than 1. So let's take a look at the solution here. Now, you see now, if we want this to be less than 0, then when we solve this equation, since all the constants are larger than 0, then what we simply must have is that epsilon is less than 1. Would you agree upon that? Does that follow from? So that follows simply from that equation. So what you see now is that if epsilon is less than 1, we have a energy which is less than 0, which means that we are going to get bound motion. So the Earth is going to rotate around the sun in a specific type of orbit. It can be a circular orbit if epsilon is equal to 0, or it can be an elliptical orbit. So let's now look at the case if E is equal to 0. So in our curve, that means that we would place ourselves, if we now just make a new drawing of it. So we have R here. So we are simply placing ourselves here, at this position here. So this is going to be our R min, our new R min. This is the smallest distance between, let's say, the Earth or the sun, or two objects which are interacting. And if you then look at the equations here, if that's the case, then what we have is that epsilon minus 1, epsilon squared minus 1 is equal to 0. And that means that epsilon is equal to plus minus 1. But since epsilon is determined in terms of physical constants, which are larger than 0, it means that epsilon equal to plus 1 is the only alternative. And this is what led to parabolic motion. So we see now from the energy, just looking at the curve here, then we can then infer from the energy curve, we can then infer that there has to be a specific type of motion. So in a way, this is bringing us back to many of these energy curves which we have plotted, where we have tried to, by watching the curve, to find what type of motion we are going to get. Now, in this specific case, it's not that intuitive to see that you would get an elliptical motion or parabolic motion, but when you do the mathematics here, you get a parabolic motion when you have an energy which is equal to 0. So this R min is the closest the two objects will get with a total energy which is equal to 0. So remember now that this energy is a balance between kinetic energy and potential energy. So it's potential energy and kinetic energy which sum up to 0. Now, remember also that when we look at the potential energy, this is always scaled with respect to some reference point. So even if we scale this to be 0, it does not mean that the total energy of the system is equal to 0. But this is relative to a specific scale, which we have chosen. So we are just looking at differences in energy. So we are not looking at total energies. Just keep that in mind, because it sounds a little bit strange that the system has 0 energy. This is the relative energy between two objects. Okay, so what about the final case? So one of the case which we haven't looked at yet is the final one here, when E is larger than 0. So if we now look at that one on the graph here, this would correspond to a position where we are here. So you could now think of a comet getting close to the sun or to the Earth, and then it reaches a minimal distance, and then it gets deflected again, and then it just leaves. So if we now take this R min, what we are going to do then is simply to take the same equations which we have, and now we have an alpha squared of mu. We are still assuming that the radial velocity is equal to 0. And then we have epsilon squared minus 1. And then we simply require that this one is larger than 0. Now, if we then do the algebra here, it's pretty easy to see that this simply requires that epsilon must be larger than 1. So we have not yet said what kind of motion we are going to expect, but with this epsilon equal to 1, if we now plug it in, if we now go back to the equation for r, which is given by this constant c of 1 plus epsilon of cosine phi, you see now that the denominator vanishes. So the denominator vanishes at some value which we can call a phi max here. And that means that what we have now is that an epsilon times a cosine of a phi max is equal to -1. So that means that this cosine of phi max is equal to -1 divided by epsilon. And in our case, epsilon is always larger than 0. No, sorry, larger than 1. So the question is, what kind of orbit is this? And what we're going to show now by some manipulations here is that this is going to lead to a hyperbolic type of orbit. So let's try to convince ourselves about that. So what we have, again, is the same equation. So we start with the equation which you see up here. We multiply by both sides with 1 plus epsilon cosine phi, and simply remember or remind ourselves that Rx is R times cosine phi. So we multiply out, so we get then R, or 1 plus cosine phi, epsilon times cosine phi, and this is equal to C. We can rewrite this as R plus epsilon times X is equal to C. R is equal to C minus epsilon times X. And then what we're going to do is just to square the equation again, as we did previously when we looked at the equation for an ellipse, but also for a parabola. So when we square it, we then know that R squared is X squared plus Y squared. And this is going to be equal to C squared plus epsilon squared times X squared. And now epsilon is larger than 1, so we leave it unspecified. -2 times C of epsilon times X. So we can rewrite this again. So we have an X squared, and then we have a 1 minus epsilon squared plus a Y squared. And then we can shuffle over to the other side, this 2C times epsilon of X, and this is equal to C squared. I can change signs and complete squares. So I can now change the signs here. So I would get an X squared, epsilon squared minus 1, minus Y squared, minus 2C of epsilon times X is equal minus C squared. And then I can complete the squares for X, as we did in the case of the ellipse. So it's just some mathematical manipulations here. Squares for X. So what I would like to have now is just I'm adding a parameter. And this, what we see here now, is going to follow much of what we did previously in terms of an ellipse. So I get an epsilon minus 1. And then I have an X minus a term delta squared minus Y squared is equal to minus C squared plus an epsilon times a C squared of epsilon squared minus 1. And what I've done is actually to add and subtract two terms. So this is the same as X squared minus 2X of delta plus delta squared. So I'm just doing the algebra here. And this delta is simply C times epsilon of epsilon squared minus 1. This kind of exercise here is also relevant for homework number 9, the final one. And I can rewrite this further. I can actually show that this delta is the same as this C times, and I'm going to introduce a new parameter, alpha. So this is the same as C times alpha. And this, sorry, epsilon times alpha. And this alpha is the same as C divided by epsilon squared minus 1. I define a parameter beta, which is C divided by the square root of epsilon minus 1. And then what I will get then is the following equation. When I plug in these definitions, I can actually show by dividing with the epsilon minus 1 squared, I can get minus delta squared of alpha squared minus y squared, not gamma, but y squared, divided by beta squared, and this is equal to 1. And this is the equation for a hyperbolic motion, or hyperbola. Should be an R here. So these manipulations are pretty easy to see. It follows very much what we did with the equation for an ellipse. So for this specific case, when epsilon is larger than 1, we get the equation for a hyperbola. And if you now want to make a plot of this, what you can do then is to actually go into the textbook of Taylor, which has a much better drawing than the one which I can ever make. And you've probably seen my poor skills when it comes to drawings. So let me just find that one. This is actually a much better figure than what I can ever make. So I don't dare to make all these kind of figures because my circles are already ugly. My ellipses are even worse, and I don't dare even to set up a parabola or hyperbola. So this is actually the so-called Kepler orbits. So when we talked about Kepler's laws, these are the kind of orbits which we get for a gravitational force, and these are typically called Kepler orbits. So you could think of a comet, so which now approaches a astrophysical, astronomical object. It could be the Earth, it could be the sun. It can be bound, and when it's bound, it means it has an energy less than 0. And then it gets trapped by, let's say, the Earth, and it would orbit around the Earth, and it can orbit as an ellipse or as a circle. So that depends again on the type of energy which the system has. Alternatively, it can have a parabola, as you can see here. So these orbits actually chosen for the same values for R in this figure, R mini. And you would then have a hyperbola, which looks like this, and that has a maximum angle where the radius goes to infinity. And similarly, you have one for a parabola. So this is a kind of motion you can read off by using the analytical solution to the radial equation for the radial acceleration. So by making this transformation to the new type of coordinates, we can then simply say that the type of motion we can read off from the energy curve for this effective potential corresponds to 4 different types of Kepler orbits. 2 which result in unbound motion. So it means that the object will leave. It will never be bound. And 2 type of orbits which correspond to bound motion. And one is a circular orbit and the other one is an ellipse. Now, this kind of analysis, which you see here, is a type of analysis which you are going to encounter again in physics courses like electromagnetism, or when you do quantum physics. When you do quantum physics, you can think of an electron which is trapped by a potential interacting with the Coulomb force. And that Coulomb force is a lookalike of the gravitational force. So classically, you can study the motion of an object which is bound by, let's say, a potential. And this potential could be a potential which is set off by an atom, or it could be a molecule or more complex object. It's like the Earth gets trapped by the sun because the sun is much more massive. The sun barely moves. We define that as the origin. And then the Earth is bound to move around the sun in something which is almost like a circular orbit. It's actually an elliptical orbit. And you can repeat this analysis and replace the Earth and the sun with charged objects. It could be electrons, an electron and a proton, an electron or an atom, and so on. And you will get exactly the same type of motion, the same way of thinking, except that when you do quantum mechanics, the energies do not take continuous values. So in the case which we have here, the energies span a continuous set of values. So there's a continuous kinetic energy and there is a continuous potential energy. So in a sense, you have an infinity of values. When you do it quantum mechanically, what you will see then is that these values are discretized. There are only some specific energies which are allowed. So that's the difference between a quantum mechanical system and the classical system. But the way of thinking we are doing here is exactly the same. So when I've been stressing this kind of way of thinking, it's because you are going to see this again and again in all physics courses. So I'm in a way indoctrinating you to think of, look at the energy curve or the potential curve. And from that one, you can say a lot about what kind of motion you may expect. Now, in this particular case, we actually need to solve things analytically, numerically, in order to extract like these 4 different Kepler orbits. But the basic physics message is more or less the same. We have bound motion and we have unbound motion. And you can actually infer that from just looking at the curves for the energy. And that's extremely useful because that is something which allows us to build up an intuition about a physical system without having run calculations. Any questions so far? So when you have this type of calculations or this kind of results, let me see if I can trigger your intuition a little bit. So let's go back to the whiteboard. So what we have been looking at is an attractive force. So attractive is normally means that you get pulled in. So this is the force which we have looked at. So minus alpha divided by r squared. It means that we have a effective potential where we have one term which comes from the kinetic energy, which is related to the angular velocity in this case, times a factor of 2. And then we have a potential which goes minus alpha divided by r. And then we know that this radial component of the force is given by the derivative of dv of d of r. Now keep in mind that we have made this transformation to polar coordinates, so we are not looking at the vectors now. Now, let me now see if I can trigger your intuition here. If you now replace this same force, but you have this sign in front of it, what kind of physics would you expect now? If you were to plot the potential, would this lead to bound motion? Would it lead to unbound motion? So the only thing we did now is to replace the sign in front of the force. This means that we have a potential which has a positive sign in front of it. So when you pull an object in, then we talk about an attractive potential and an attractive force, because you are pulling in, there's an attraction. If you have a plus sign in front of it, you're repelling something, so you're pushing things out. So if I now take a potential which is not attractive, but repulsive, what kind of motion would you expect? Can this lead to the same things as we saw with the Kepler orbits? Or are we much more limited? Yeah?
would be like an unbound orbit, right?
This would only be unbound, because when I plot now the potential, this would be something which, if I look at the two objects, so if we plot it, so let's just write it down. This is unbound. Now you can solve the differential equation, however, and this differential equation is going to give you an analytical solution as well, because you have the same type of force. And one of the things you're going to see is that the equation here just changes a little bit. It's going to have the same constants, but it's going to have a positive sign here, cosine phi, but there's going to be a -1. And if I plot the two quantities, this potential itself, so I plot the V effective here, there's going to be one term which goes like this. So this is my plus alpha divided by R. And then there's going to be another term which drops up a little bit faster, which is going to be this term. So this is my L divided by 2 mu over R squared. But what you see now is that the energy is always going to be positive, which means that if you have a case like that, you will never get a bound motion. So this would be a system where the objects can get closer to each other. So we can still, so remember again that this is a relative motion. So this is a relative distance between two objects. We can always get to a point here where they are getting close to each other, but the system will always be so that it will never be able, the massive object like if this was the sun, it would never be able to have the Earth in a bound orbit. So by just looking at the potential, you can already say something about what kind of physics you may expect from this type of system. So on Wednesday, I will wrap up a little bit about these things, and I will show you some more examples and how we can relate this to one of the homeworks, and also how we can relate this to the midterm. So on Wednesday, I will discuss a little bit more about the midterm, in particular, how you're going to add planets like Jupiter and what kind of equations you need to set up. And then we're going to look at an applications of this to scattering. So scattering is extremely important when you're looking at reactions in physics. And you can use much of the same machinery as we have here. Okay, I'm going to stop here. And feel free to hang around if you have questions about exercises or other things.